hope you're doing well. My name is Shireen Ali, and today I will be presenting my assignment 4, which focuses on identifying and reducing overfitting in a convolutional neural network using the Assignment04 image dataset. In this assignment, I demonstrate several important deep learning concepts that we have learned in class, including data preparation, regularization, data augmentation, and performance evaluation. And so here we began with importing the required libraries. I used TensorFlow and Keras for building and training the CNN model, Matplotlib for visualization, and NumPy for numerical operations. These libraries are essential for working with neural network and image data. So let's begin with, and so the next one, I loaded the Assignment10 dataset. It contains 60,000 color images in categories such as airplanes, dogs, and cars. I split this data into training, validation, and test sets. I also normalized the pixel values of the image by dividing by 255. This is a crucial step because it helps the model train faster and more efficiently. I kept 80% of the training after the training data for actual training and used 20% for validation. This split allows me to monitor how well the model generalized during training and detect any overfitting. And here, let me just... And one of the biggest tools to fight overfitting is data augmentation. In this cell, I created a data generator that applies random transformations to the image, like rotation, zooming, flipping, shifting, and more. This helps the model learn from more variation of the training data and not just memorize a specific image. This technique increased the diversity of the training data without needing to collect more images. And now into the model, I use a sequential model with 3 convolutional layers followed by max pooling layers. These layers help the model detect features in the image like edges, textures, and shapes. To prevent overfitting, I use L2 regularization in 2 of the convolutional layers. This technique penalizes large weights in the model, helping it generalize better. After that, I added flatten layer and dense layer, followed by the output layer with softmax activation, since this is a multi-class classification task. And then I compiled the model using the Atom optimizer and sparse categorical chronology as the loss function. I trained it for 10 epochs using the augmented training data. As the model trains, it also evaluates its performance on the validation set. This helps us track whether the model is learning well or starting to overfit. And then after training, I evaluated the model on the test set. This accuracy I got shows how well the model performs on completely unseen data. It's a good measure of how well the model generalized beyond the training and validation set. And now, so let's go through the required graphs to analyze the performance of the model and detect overfitting. So in here, this is all the graph, so the first graph compares training and validation accuracy over each epoch. Ideally, both lines should go up steadily and stay close together. If the training accuracy is much higher than validation accuracy, it's a sign of overfitting. Yeah, it's loading. And in here I plotted the training accuracy by itself. It helps visualize how fast and how well the model is learning from the training data alone. You can see how it improved with each approach. This fourth graph. The fourth graph shows validation accuracy by itself. This helps us see clearly how the model performs on data it hasn't seen during training. If it increases steadily, it's a good sign. Yeah. So as a bonus, I included 2 more graphs, one for training loss and one for validation loss. These offer deeper insight and are especially helpful if the model's accuracy looks good, but the loss tells another story. So this is all the coding for this assignment, and yeah, that was it. Thank you so much for your time.